Good afternoon, everybody, and welcome to another Alliance for PE Pipe Roadshow Light program. I'm Drew Mueller with the Alliance for PE Pipe, and today we are bringing you our good old HDPE 101 presentation. We've given this presentation more than just about any other. Up until about a year ago, we traveled all over North America presenting this to municipal folks across the United States and Canada, but we're happy to bring it to you here on Roadshow Light today. So before we get into the talk, always need to take care of a few housekeeping items. First of all, we want to thank all our members today. These companies fund the Alliance's operation. If you want the best pipe, fittings, and equipment for your projects, purchase from these organizations. In particular, today, we want to thank special thanks to Footage, manufacturers of squeeze-off tools in particular, but lots of other tooling. Ben Ferguson from Footage is on the call today. Ben, do you want to come on the air and just say a few words about your company? Hey, Ben,
Thanks,
how are
Drew.
you?
Good, thanks. How are you?
Doing well, thank you.
Good.
So tell us about Footage squeeze-off tools.
Yeah, for sure. So my name's Ben Ferguson. I work for Footage Tools, as Drew said. So we've been in the manufacturing space for just under 40 years. And we're probably most well known for our squeeze-off tools, where we have tools all the way from 1/2 inch through 16-inch pipe. And we also have a steel line as well. We do several other, manufacturing products as well as underground piercing tools, tapping tools, and a few other lines. But yeah, just thanks for being on the call, everyone. Really, for this, we just want to really shed some light on squeeze off within the industries and multiple industries. And I think we're most known for the gas utility space. However, just spreading the word that we can squeeze PE pipe safely and effectively. So thanks to the PE Alliance, and yeah, excited to be on the call.
Great, thank you. Yeah, squeeze off, it's easiest to squeeze off polyethylene. It returns to form. We'll talk a little bit more about that technique later in the presentation, but Footage tools, they are the best for this sort of thing. Moving along, if you want to join the Alliance, you can do so on the website pepipe.org. There is no cost to join if you're a contractor or an engineer. If you're a manufacturer, there is a small fee. Follow us on social media. We're over 15,000 followers on these 4 platforms combined. LinkedIn is where we see our most action, but follow us on the platform of your choice. Also on that website, pepipe.org, we have a great case study database. It's searchable by project type, by geographical location. So if you are considering a poly project, chances are you can find somebody nearby who's done something similar in the past. We have a few more upcoming Roadshow Light programs, and you can register for all these on the website as you did for today. Tomorrow, Alan Ambler and Richard Colosso will be presenting HDPE 101. Peter Dyke, thank you for joining us today. Do you have something to say?
Oh, Drew, it's always good to have you behind the controls, and welcome everybody to another Roadshow Light. And I looked at the list and I'm so excited that there are a lot of familiar names, and many people, like 25 of the people, have already sat through this 101, Drew, at another point in time, and they're back for more. And I've said forever, that second time you watch this show is you can learn almost as much as the first time. And reinforcement is so important. So I encourage you, tell your colleagues about this and that we do these 101s. The first time this year we've done it. Alan Ambler, come on the line. I would like you to tease the above ground talk, because this is the first time we've given this, because everybody's asking about above ground with frequency. Alan, welcome.
Hey, thank you very much, Peter. Glad to be here. Yes, I've been very much enjoying pulling together the presentation on above ground installation that'll cover the majority of things that people work with by shipping to the site, receiving the pipe, how to store it, how to make sure that it's carefully protected prior to installation underground, but then also on bridges and supports and temporary connections, such as temporary bypass for pipeline rehabilitation projects. So we're going to cover the nuts and bolts of all above ground installations from A to Z, and I look forward to the presentation. That'll be March 10th next
Yeah,
week.
awesome. And then after that, the week after that, Drew and I are going to head down to Tulsa and meet with McElroy and get to know some of their products in an in-depth 75-minute session. McElroy owns the market for butt fusion machines here in North America, and this is the first time we've taken the opportunity to get to know them in a full-length webinar. Drew, back to you.
Yeah, that McElroy show is going to be pretty exciting. We're going to demo machines from a small diameter manual machines all the way up to the new large diameter track hydraulic machines with a fully automated fusion process. So I'm really looking forward to that one. You can register again for all these on pepipe.org. Moving along, a couple resources we offer for you. The engineers package. We haven't updated it for 2021 yet. We will soon. If you are designing or working with polyethylene, this is a great resource for you. The Alliance's model specifications, standard details are included in that package, as is this book on the right-hand side of that picture, the Plastic Pipe Institute's Handbook of Polyethylene Design. I reference the book just about every day when I get technical questions. Again, if you're designing with poly, you want this resource, shoot me an email, dmueller@pepipe.org, and I will send it your way. We also want to plug the Poly podcast. This is our polyethylene podcast we started producing about 6 or 7 months ago. We're putting out 2 episodes a month, going in depth with engineers in the polyethylene industry, as well as municipal engineers who have embraced use of polyethylene and how it's impacted their systems. It's been a really fun project, and you can find that anywhere you download your podcasts. Any further questions we don't get to, you could shoot any of us with the Alliance an email. Got Richard Colossus' name on there from WL Plastics. He was a last-minute scratch today. Alan is his replacement. But we encourage you to ask questions during the show using the question tab. Alan and Peter will be fielding those. Again, we'll get to as many as we can. If we don't get to your question, please shoot us an email. All right, now we're ready to get into the heart of the presentation here, HDPE 101. Well, we start with a picture of Peter and Alan at President Obama's White House Water Summit a few years ago now. They kind of walked into a room looking like this, a lot of intelligent individuals talking about how they can source water for their municipalities. So some of these are pretty straightforward. New dams, yeah, I understand that. Rainwater harvesting, okay, makes sense. Desal is an interesting one. Like, yeah, that'll add water to your system, but it will do so at a significant cost. City of San Diego completed a desalination plant a few years back. They spent $1 billion on that desal plant, and it added about 7% to their water system. It's estimated that they could have spent $400 million, converted their entire system to HDPE, and actually added 10% to their water system by eliminating all water loss due to leakage. Icebergs, that one seems crazy, but there are countries in the Middle East considering hauling icebergs from Antarctica to the Persian Gulf to supply clean, fresh water to their citizens. But Peter and Alan, they kind of felt like the waiter. You know, they're looking at this list of ways you can add water to your resource, and they're thinking, why not just eliminate the leaks? So a little bit of background on HDPE use. 1959, that was the year of the first polyethylene installation in the United States. There was a gas line in Kansas. 2.1 trillion, that would be the gallons of water lost by municipal water system leakage in this country every year. 240,000, it's the number of water main breaks in this country every year. This year, given the weather we've seen in the southern states, that number is probably going to be a little bit higher. And we're going to see in a little while how polyethylene solves for that issue. 14%. That would be the average water loss rate, according to AWWA, for municipalities in the United States. We were in Missoula, Montana a few years ago. Their water loss rate is 48%. That's 48% of the water that's been sourced, treated, pumped out of their treatment plants is lost into the ground due to leaking infrastructure. Niagara, New York, same thing. Their water loss rate is right up there around 50%. The story in Niagara, New York, they have a big river. It's cheap and easy to source water. In Missoula, the story there is kind of interesting. The water utility and the electric utility used to be owned by the same company. Who's the biggest power user in most cities? It's the water utility because they're running their pumps 24/7. So when the electric and water utilities were owned by the same company, they weren't particularly concerned about all the energy they were wasting pumping water into the ground. Peter, go ahead.
Well, so the backstory on that White House event that Alan and I attended, Drew, is that, I pitched that we're leak free, we don't have joints, our classic argument that should appeal to civil engineers. Yet they told me afterwards the reason we're accepted as the only pipe type was for that reason, Drew, that you mentioned, is that the utilities, because they use most of the electricity in town, they're the biggest user, we have the lowest carbon footprint on electricity because we're not pumping water into the ground like Niagara and Missoula does. In fact, we pump a lot less. The pumps are on less because we don't have as much leakage in polyethylene systems.
Thanks, Peter. 1.4 trillion. This is a really interesting figure. ASCE tells us this is the budget shortfall between what municipalities are spending to maintain and rehabilitate their water systems and what they should be spending to maintain and rehabilitate their water systems. Pretty significant number, major budget shortfall. It tells me that 2.1 trillion gallons of water lost, 240,000 main breaks, 14% water loss rate. Those figures are going to continue to rise as we continue to neglect our municipal infrastructure. And finally, 18,000, that would be miles of HDPE installed for potable water in the US last year. So why use HDPE? We have a whole list of reasons here. We're going to touch upon all of them throughout the day today, but we always start by talking about polyethylene's superior seismic resistance. When we used to travel and do this presentation, we would go to places where people didn't really care about seismic events. But you know what? There's ground movement in every single part of the country, everywhere you go. It might be freeze thaw, it might be soil compaction. And if polyethylene can withstand the most violent type of ground movement out there, those other types aren't going to be a problem for the product. So let's take a look at a couple studies. First one, the Water Research Foundation hired these two guys, Edinger and Davis, to travel around the world and look at the aftermath of some major seismic events. First place they went, Concepcion, Chile. Back in 2010, they had an 8.8 earthquake, pretty significant. What's interesting about this case is that SBO, the public utility in Chile, they had begun replacing pipelines with polyethylene back in 2001. So almost a decade of polyethylene use meant there's a mixture of materials in the ground made for a good comparison study for Edinger and Davis. So 8.8 earthquake hits, major damage above and below ground. Edinger and Davis could not find a single HDPE failure as a result of that quake. Christchurch, New Zealand. This one's interesting because it's not one major quake. It's 4 6.0 spread out over the course of 15 months. So first quake hits, the mayor of Christchurch and his public works director, they're sitting down kind of assessing the damage, trying to figure out a plan, how they're going to move forward with repair and replace. Public works director says, well, we got a lot of damage to our water and wastewater lines. Gas lines are totally fine. The mayor wanted to know why. It's because the gas in New Zealand, as it does in this country, is running through medium density polyethylene pipe. Long story short, mayor convinces the public works director to do some pilot projects, some replacement projects with polyethylene for water and wastewater. Along come quakes 2, 3, and 4. And as was the case in Chile, no damage to those new HDPE lines as a result of the subsequent quakes. Finally, Japan, 9.0 earthquake, one of the most significant seismic events ever recorded, 600 times more powerful than the atomic bomb. Just like in Chile, there were mixture materials in the ground. Edinger and Davis could compare polyethylene to PVC to ductile iron. And as was the case in the other two examples we've looked at, not a single HDPE failure as a result of one of the most significant earthquakes ever recorded. So to summarize, 3 major seismic events, billions of dollars in damage, lives lost, total mayhem above ground and below ground. The common denominator in all 3 cases, not a single HDPE failure. So that's all international data. Let's get a little bit closer to home. Napa, California, 6.0 earthquake a few years ago. City of Napa experienced 132 main breaks. They do not use HDPE. Coterminous to the City of Napa, so same customers, same distance of pipeline in their system as Napa Sanitation. They use a lot of HDPE. Same earthquake, same place, not a single failure because they're using polyethylene. Trona, California, just a couple years ago, 7.1 earthquake in San Bernardino County. Trona does not use HDPE. They experienced a lot of failures as a result of that quake, 7.1, pretty significant. What's interesting, in the same location, PG&E, the electric utility, and Cero, which is a mining company, they have hundreds of miles of polyethylene running, same place, same quake, no failures. Peter.
So what we look at as a failure in this case, Drew, would be a fusion separation or a crack. Hey, Alan, come on the call. And I interviewed a crew that was responsible for making sure those gas lines were still okay, Drew. And this one guy pulled out a photograph on his PG&E handheld that was a 4-inch polyethylene line that went under a road, Alan, and it actually moved about 3 feet under the ground, and it didn't come back to its original location in the ground. So it went beyond yield, but it never leaked. Can you explain that to me, Alan, and why we don't count that as a failure?
So the polyethylene material itself won't be counted as a failure in those scenarios, even though it did go beyond yield, because it still is able to convey the material that's within it at that time. So that obviously, for a long-standing installation standpoint, we obviously want to know where those locations are and go in and perform a repair and remove the yielded material. But from a temporary standpoint, you could still pass and convey material within it,
Yes.
even in that scenario.
So what they did is they cut out that damaged piece. They squeezed off the two ends, cut out the damaged piece, and used electrofusion couplers to repair it. So Drew, it's a really good example of, here's a county and a city, Trona in San Bernardino County, that don't use it. Lots of failures in ductile, replaced it with PVC, no polyethylene failures. So now we have domestic data that supports all that international stuff.
Mm-hmm. Yeah, thanks, guys. So polyethylene seismic resistance. Why is it seismically resistant? Well, number one, there aren't joints. It's not a bell and spigot system. We fuse the pipe together, two pieces of pipe. Once they're fused, it's essentially one pipe. That fusion is actually stronger than the pipe wall itself. We'll talk about why in just a moment. The other reason it's seismically resistant is because it's a flexible product. This guy on the right's about 6 feet tall. He's standing in front of a 400-foot spool of 6-inch HDPE pipe. Rural water systems, they love this. That's a lot of fusions they don't have to do for their long runs. I don't think you can coil up ductile iron or PVC quite like that. Poly's the only product we can do that with. Let's look at another study here. This one, Dr. Thomas O'Rourke from Cornell University. He and his grad students built this big trench box. So if you look at that picture on the left, one side of that trench box is stationary. The other shifts 4 feet to simulate the fault line in an earthquake. They had a stick of polyethylene running across that fault. There was even a fusion in that 35-foot span of HDPE. Let's see what that looks like inside the pipe. You can see pretty significant movement. That pipe did not fail. So again, 4-foot shift simulates what happens in an earthquake. So if pipe was displaced like this in an earthquake, if it didn't reach its yield point, when a repair crew excavated it, de-earthed it, however you want to describe that process, it would slowly regain form, return to that straight line shape. The pipe is extruded in a straight line. It has a memory. It's flexible, but it wants to return to the shape in which it was produced, that it was extruded in. Peter, do you want to tell us a little bit about the history of pipe, water material, water conveyance material evolution over time?
I suppose I could.
Well, I don't want you to do anything you're not comfortable doing, Peter.
Before we do that, I have a question. Drew, I mean, I see a lot of great advantages of polyethylene. What are two disadvantages of the product? Now, I'll go do one. The first is This is from an engineer out of California. We recommend that you use qualified operators. One of the things we learned from the gas industry, which is all polyethylene on distribution, 99% of it anyway, is that you've got to use trained operators. Fusion is a little more complicated. That process is a little more complicated than putting the bell and the spigot together in the trench. And we want in your spec to say you must use trained operators. Drew, you got another one?
Sure. Yeah. HDPE can't convey hot water, but for municipal water and wastewater, that's not an issue. You talked about failure because of improper fusion procedure. The other failure mechanism we see would be third-party damage. Polyethylene being softer is susceptible to cross boring. The drill operator isn't going to feel that he's drilling into polyethylene the same way he would if he hit a metallic pipe. But you know what? You're supposed to locate all those crossing utilities ahead of time anyway.
Well, we all know that that's difficult to do though, Drew. So there is a priority placed on using good information and checking the route before you do it. But you know what? We have good data on this, Drew, and that is mortality rates in the gas industry. So the gas industry people showed up one day and they said in the 70s, you shall use polyethylene. So this is the American Gas Association. And they've seen a steady drop in mortality associated with pipeline failures since they've gone to a plastic pipe, namely medium density and now high density polyethylene. So this whole argument about polyethylene and pipe types, as you look at it over time, just look at pipeline conveyance materials over time. We started with open trenches before Christ. We went to wood, we went to clay, we went to lead, we went to cast iron. The cast iron that's 100 years old is a very robust material. In many cases, it has outlasted ductile iron. We see asbestos cement. It had a good 50-year run. A lot of people don't know why there was asbestos cement in the ground. It's because during the war, we couldn't get metal. So we mixed asbestos fibers with concrete and cement, and we came up with AC pipe. No better way to get rid of that than with polyethylene and pipe bursting. And then we have ductile iron, PVC, and polyethylene that were all commercialized in the mid-1960s. So all three pipes have been around about 50 years. But Drew, as you know, polyethylene didn't go after the water market originally. What's the dynamic there? Why didn't we do that? And why did we let ductile and PVC come in and gain so much market share?
Yeah, so it's kind of interesting. Ductile, PVC, polyethylene all came online within about a decade of each other. PVC and ductile, being bell and spigot systems, were seen as a natural replacement for cast iron. So they entered the markets where cast iron dominated, water and wastewater. Polyethylene, being a fusible system, seemed like a natural replacement for welded steel pipes. So they entered the market where welded steel dominated, oil and gas gathering, heavy industry, mining. And they, all three pipe types took over the markets they chose to enter.
So we just got a question come in, Drew, and the question was, are we going to make this presentation available? So what's the procedure for that, Drew?
Yeah, shoot me an email, dmueller@pepipe.org, and I will send you a copy of the video of this presentation or the slides, whichever you'd prefer.
So Alan and I participated in a roundtable with PVC and ductile iron last month up in Maine. And, the argument the gentleman from the ductile iron world said was, our product is so good in the last 50 years, we haven't needed to improve it. Whereas the polyethylene people, you have to keep making it better and better. Alan, can you comment on that?
Oh, most definitely. In that 50-year time period, there's been a lot of changes. Trenchless technologies have come forward to be one of the primary growing industries to rehabilitate existing pipeline. And right now there's few examples of installing a bell and spigot pipeline through a trenchless method. You do have some options for you, but high density polyethylene solves for the three primary causes of failure, which are soil displacement, corrosion, and then long-term fatigue. So those innovations within the polyethylene industry that gets us to the fourth generation, and then all of the fittings that really have been developed for the pipeline are really a shining star for polyethylene.
So I was kind of struck by that, and we'll have a slide later on that talks about the evolution of the polyethylene resin that makes this fantastic pipe. And we're about to move beyond this benefits of the product to get into some more interesting stuff. But I created this slide last week during the height of the freezing events that occurred in Texas and Oklahoma to illustrate in Tulsa, which is our corporate headquarters. So it's kind of near and dear to my heart. And we really haven't been able to conquer that utility. They love their ductile iron. But here is a utility that really struggled. I mean, they had close to 200 water main breaks in a 6-day period directly as a result of the weather. And to that whole issue of seismic performance, which is the ultimate in ground movement, here we have less ground movement from a comparison standpoint, yet a tremendous impact on this utility. They're still making fixes. Alan, could you give us a little color on this slide?
Yeah, absolutely. I saw a bid shortly after these breaks too, where they were going out to find contractors to help with the emergency breaks itself. So cold water, as we could see, or cold temperatures wreak havoc on water systems that are simply not used to it. We were talking with our friend Richard Kalasa, who's in Calgary, where they're used to this, and they didn't have any failures when they experienced -40 temperatures. But in high density polyethylene pipe, that water within that pipeline, if it's stagnant, which is what freezes. So if there's water sitting in the pipeline and not moving, then it becomes stagnant and can freeze. It will expand the high density polyethylene temporarily, which can accommodate the expansion. And then once that water movement starts to go, obviously, then you'll start to bring warmer water to it and start to melt those ice particles. Obviously, it's not going to go through a pump. Any kind of ice blockages needs to be removed before it goes through a pump or a service connection. But yes, high density polyethylene can tolerate expansion due to frozen water within its system.
Yeah, without failure. And we have plenty of data on that. Just so you all know, Alan Ambler is a engineer. He's a PE. He does consulting work with us at the Alliance. He wrote the book on trenchless technology, the third edition for NASTT. Got 10 years working for a municipality. And he's also done the largest pipe bursting project of AC pipe in the United States of some 45 miles. Did I get that right, Alan?
The book is specifically on pipe bursting, not just all trenchless technologies. But yes, you did get it right. Good job, Peter.
Oh, thank you. Oh, so speaking of a city that does get this whole polyethylene thing, here we have an interview I conducted earlier this week with Eric Schaefer at the city of Duluth. So a little colder climate.
Big things are corrosion leaks. Over time, a number of leaks and water main breaks we had each year just kept spiraling up and up. And we define a leak as a water coming out of the pipe that we can fix anytime we get to it. Where a break is something we can call an emergency, fix it right now. But we got as high as about 160 leaks, 160 breaks, or a total of 320 holes in the ground up in 1 year. Now we're trending back down finally now. But that's because we've gone out and focused on the worst neighborhoods. We pulled out the cast iron and the ductile iron and stuck in polyethylene, and we just don't have failures anymore.
Peter, can you try running that with your volume turned up a little bit? A couple people saying they can't hear.
Turn on the volume of the TV. Let me see.
On your computer, just turn the volume up.
All right.
Cut it to a third, but some of that's affected by temperature. I can't take all the credit.
But you had some breaks. Were they in polyethylene?
Big things are corrosion leaks.
How's that, Drew?
Time, a number of leaks, water main breaks.
That's better. Thank you.
Here just kept spiraling up and up. And we define a leak as a water coming out of the pipe that we can fix anytime we get to it. Where a break is something we call an emergency, fix it right now. But we got as high as about 160 leaks, 160 breaks, or a total of 320 holes in the ground up in 1 year. and we're trending back down finally now. But that's because we've gone out and focused on the worst neighborhoods. We've pulled out the cast iron and ductile iron and stuck in polyethylene, and we just don't have failures anymore.
So you used to see at most 320 a year. What are you looking at now on an annual basis?
Last year we had 127 leaks and breaks combined.
Wow, so you've cut it to a third.
We cut it to a third, but some of that's affected by temperature. I can't take all the credit.
But you had some breaks. Were they in polyethylene or were they in traditional materials?
Traditional materials. Yeah, we don't have breaks in polyethylene.
All right. Okay, Drew, can you hear me now?
Sure can.
Awesome. All right. So this is what, we have a new definition of sinkhole going on here in North America. That's when cars fall in the holes created by failing pipes. We don't see that with polyethylene. In fact, the utilities that were in Texas and Oklahoma that use polyethylene did not see failures in their HDPE. Classic failures with PVC, over insertion, and as Alan mentioned, cyclic fatigue. Polyethylene does not fail with cyclic fatigue. Fatigue is not an issue with polyethylene. So both traditional materials, PVC and ductile, have allowable leakage rate. Here we have an example of 460,000 gallons in PVC, according to AWWA's M23, allowed in a 12-inch line in every 10 miles per year. So polyethylene solves for tuberculation. It doesn't crack circumferentially like old cast iron does. We don't have an over insertion issue. To that one engineer's point, we do have a fusion issue. We got to make sure our fusion operators are qualified. We also have the lowest operating cost because we don't see failures toward the end of the product's life. And we like to argue that we are best in class. We are a best practice because this procedure has been shown by research and experience to produce optimal results. Now let's look at some current events. Google, Apple, Tesla, with their new facilities, their new corporate headquarters, have all used polyethylene. The Wall Street Journal reported in this article here on the right that the hell of man built what we're calling a beer main to connect the brewery to the bottling plant so that the mayor wasn't irritated about all the beer trucks running through his beautiful town in Bruges, Belgium. So the big issue 3 years ago now in Cape Town, South Africa, they're building 7 desalination plants. What are they running out to the ocean with their brine and also their intake lines? Polyethylene. You're not going to use PVC. All those pipes on the side of the road, those black and orange pipes that you see when you're driving by, they're horizontal directionally drilling. Are they going to use a bell and spigot system in conduit lines? Of course not. Yet we continue to use and put up with leaks and cyclic fatigue in bell and spigot systems because that's what we're used to. Times are changing. Plastic Pipe Institute wrote a great article 2 years ago now about the fires in California. And now Paradise, 2 years after the fire, have announced that they're going with polyethylene for their mains and service lines. The ocean cleanup, these guys that are tackling the plastic in oceans, what are they using to operate their boom? They're not using a bell and spigot system. They're using polyethylene on their boom because polyethylene floats. So we are a leak-free system. Yes, we will float in water. And the beauty and the magic is illustrated right here in this little video where we're taking 2 shaved, heated ends and sticking them together and creating that double rollback bead. And this is what your spec needs to reflect, that the operators that are doing this work are properly trained to ASTM F2620. Clean it, shave it, heat it, fuse it. We're going to go into this in much greater detail on March 17th. Sign up for that event. A lot of you folks out in California love to remove your beads. So they're external beads or internal beads. They may be removed. This is a bead removal tool from R&L Manufacturing in Camas, now Vancouver. I guess they just moved, but it's very simple. You stick it down the shaft all 50 feet or 40 feet, go counterclockwise for 1 revolution. That head pops out and you can remove that interior bead. Exterior beads are a little easier to remove than that. Another common way, 90% of your fusions are going to be butt fusion. Another common way to connect to that main is electrofusion. Great way to connect to the main and connect those services and laterals. Common practice, but it results, statistically, fewer of your fusions are going to be electrofusion versus butt fusion. It's permanent. This joint is stronger than the pipe wall itself. We have data to prove that. We want you to use trained operators, follow the rules. We don't want you to use polyethylene if you're not going to follow the rules. One of the things we've learned from the cases and talking to the utilities that have adopted the product and fully integrated it over time is that they made mistakes in their first couple of years. They didn't follow the rules. That's why whenever you go to one of our events, the first things we say is use trained operators and use our distributors, Core and Main, C-Core, Consolidated, ISCO, use Sandale, use these companies because they all have trained operators, some very talented people that can teach your staff and your contractors. That guy that we just showed a video of, Eric Schaefer in Duluth, his staff qualifies and pre-qualifies any contractor that bids work, whether they get it or not, annually in Duluth, Minnesota. So does Austin, Minnesota. So does Palo Alto. So does Lago Vista. So does Miami-Dade. All these utilities are using qualified operators and they follow an established procedure. Give us an opportunity to edit your spec. Email it to me or Alan Ambler, and we will edit your spec free of charge. So what is electrofusion? This is a coupler example on your screen presently. And there's cold and hot zones. So the hot zones are in the middle there with the stripe banding. And the cold zones create dams so that when that copper wire heats up the OD of the pipe and the ID of the coupler, they get up to 450 degrees, it melts. And those cold areas hold that resin in place until it cools and we get a super strong fusion. So electrofusion is really quite wonderful. It works, but you got to do the prep properly. So here we have a Central Plastics George Fisher electrofusion processor heating up the right side of a coupler. And after this guy's done this side, he's going to go ahead and fuse up the second side. So this is probably an 18 or 20 inch diameter coupler. On the smaller ones, it's a single electrofusion. On the bigger ones, it's two separate electrofusions. And he's got what's known as a mechanical joint adapter prepared to connect up. Excuse me, that's a flange. So polyethylene is impact resistant, as my buddy Drew likes to say. Hey, the teeth of a bucket, no guarantees. But if it's the back end of that scoop, polyethylene is going to hold on just fine. You're not going to see these kind of failures with polyethylene. On the right side of this copper mine image, we had a mass wasting event. There are two guys on the right-hand side pointing at that 20-inch polyethylene fire line that's got at least two fusions in it. And even after this huge multi-hundreds of ton mass wasting event, that fire line is still in place. Now, here's a guy that didn't get the memo, didn't want to move his BMW, wanted to do it on his own time. So what do we do on this pipe burst string? We just picked it up. Thank you, Murphy Pipeline, for that video. They're a great one to follow. We're also good to follow on social media. We got videos like this all the time. And here we have another Murphy Pipeline image of a 12-inch polyethylene line going in down in Florida. And it shows the minimal disruption. Yeah, this guy's kind of irritated because he's got this pit dug. In a day and a half, he's going to have to deal with that. But that whole block face, that's a single 2-day event where this 500-foot run is done in a pipe burst. So it's really quite wonderful. So Ben Ferguson, so here we have, come online, here we have a footage squeeze tool. Ben, can you tell us why and how squeeze off is a thing and why we should consider using it in the municipal world?
Yeah, I think it's like you touched on before, there's ASTM standards that the manufacturer, we have to adhere to when designing tools, and also when the operator is squeezing off pipe. So there's a whole bunch of safety aspects that go into squeezing off pipe. And I think it's as far as the speed, so you can access a leak or any type of situation where you have control, any type of medium downstream, you can access it quickly. It doesn't take very long to squeeze, and it's very safe.
So on a, that looks like probably a 10-inch line, what are the rules for the squeeze down and then the release?
Yeah, so there's, you got to follow the ASTM standards, which says 2 inch per minute on the squeeze down, and the release is 1/2 inch per minute on the way up.
How do people get one of these things? Can they rent them? Do they have to buy them? What's the deal?
There are rental locations out there. I'd say the best opportunity if you're interested in learning a little bit more about these tools, contact me direct at bf@footage.ca, and we can send you to the nearest distributor, but we can definitely help you out.
Awesome. So the footage tool on the left there, Ben, what size is that? And how do I go from like a 4-inch to a 6-inch? What's the routine?
Yeah, so that the squeeze off tool that you'll see, the footage, the orange and black one, that's a 4-inch to 8-inch C850, and that's powered by hydraulics. And we go as large as 16-inch and as small as 1/2 inch. So it really just depends on the SDR and the diameter of the pipe, which you would fit your tool for whatever pipe you're looking to squeeze off.
So we carry one of those on our truck, Ben, as you know, and it's one of the demos that we do live that people love the most. So what we talk about is in the municipal setting is we like to see if you have a failure in a downstream line and you don't have a valve nearby, go ahead and squeeze it off. And if you're flooding people's basements, go ahead and do it quicker than what Ben says at 2 minutes for every inch of diameter. Just know that you got to come in and put a Hymax on there afterwards and then drop in a spool piece when you have time to fix it. Because if you do exceed that PPI guideline of 2 minutes per inch of diameter, you will damage the polyethylene and it will not hold pressure like we say it will.
That's right. Yeah. And the nice thing, just to one quickly, we have a built-in, we call it a CRV, controlled relief valve,
okay,
on our hydraulic unit. So you can actually control that release rate. So you're in accordance with ASTM standards. So basically, the tool will control that rate for yourself.
Awesome.
So another nice feature.
Thank you for that.
Thanks, Pete.
So one of the things we talk about a lot is we tend not to talk pressure class. We're starting to do more of that so that we can, easily communicate with people that are used to dealing with PVC and ductile. But typically in the water industry, we see DR11 for water applications, regardless of pressure class. So DR11 for us is a 200 PSI pipe that takes surges to 400 PSI. We also are starting to see DR7 on complicated horizontal directional drills. So the engineer knows contractors beat the heck out of our pipe. So they go for a thicker wall polyethylene. So while it's not a standard, DR11 is the practice. A lot of guys say, Dyke, why are you talking about DR11 when all they really need is a 21? Because nobody specifies it. All the engineers in the world, in North America anyway, rarely will go 13.5 or 17 for water. They just all say 11. So that's what I say. Why fight City Hall? But it's important that you understand surge. So with us, a 200 PSI DR11, even though you're only operating 100 PSI water system at your high working pressure, let's say you have a 60 PSI surge, 100 plus 60 is 160, you still have on the normal, you still have 40 PSI plus another 240 on an occasional surge basis. So it's really very robust pipe. And then on a DR7, which is very common in the oil patch, we see 335 PSI or surge at 670. Alan, could you come on and tell us a little bit about the evolution of the resin and why we're so excited about this and how we're honestly kind of shocked that the ductile folks look at it as a negative that we've improved our product over time and gone from series 1000 materials up to present day 4710s.
Sure. So resin in particular is how the pipe then becomes extruded. Obviously, it's the foundation of the pipe material type. Chemical engineers have been reinventing this over many, many years. So they've beefed up side chains and the ability of the pipe to have viscoelastic properties. So those viscoelastic properties allow it to temporarily deform, as you've seen, or at least change shape and not go beyond the pipe wall itself. So they've developed that to increase the mechanical strength, stiffness, and hardness. Chemical resistance, resistance to chlorine is now developing as well. They're moving the whole product to a CC 2 and 3, which are higher strength of chlorines. And the industry on whole is just growing and developing. So they've constantly moved to a better product, and that's from the manufacturing and from the raw chemicals all the way to the pipe.
Tell us about those black specks that we see in that raw resin mix.
That 2% carbon black is all that's required to make all of the UV radiation dissipate through the pipe. So you can leave this pipe outside forever. Essentially what that 2% carbon black does is takes the UV radiation and turns it into heat that is subsequently transferred and absorbed throughout the pipe. So it doesn't degrade, and it doesn't have a gasket, obviously, that degrades if it's above ground. So you could buy a bunch of this and store it in your inventory yard. And if you do require repair or something like that, then you have pipe to go for to replace it. But as you've heard from Eric in Duluth, they don't have any polyethylene failure. So save it in your yard for the next replacement project or the next new PE project that you're going to do.
So we interviewed Eric Schaefer for one of our podcasts, Alan. That's where I got that clip that we showed earlier. And he's just a wealth of information. He also, Alan, sits on the Municipal Advisory Board of the Plastic Pipe Institute. Could you tell us a little bit about the MAB and how it can serve as a resource for our audience?
Sure. The Municipal Advisory Board of the Plastic Pipe Institute is a group of individuals that work with polyethylene at the actual utilities. So I'm on that board as well with Eric, and we get together and talk about the problems and innovations that we've experienced with polyethylene pipe and share stories. So a lot of that activity really is starting to release new manuals on electrofusion, on HDPE inspections, on all sorts of things that really benefit the industry, and is a very useful group to be able to help provide guidance for actual utilities that work with high density polyethylene pipe.
So one of the documents, Alan, that the MAB has produced, and there have been several, with the guidance and direction of Camille Rubiez, who's a very learned engineer on polyethylene, that was released recently, that I'm talking about, Alan, is the repair manual. Could you tell us a little bit about that repair manual and why it's beneficial?
The repair manual is there to provide guidance on all the options to do so. So one of the keys of success for fusions are to make sure that you have dry areas. When we have water main breaks, there's a lot of water in that instance. So a lot of the knowledge and information that is pulled from gas leaks revolve around squeeze off tools and other things to be able to make sure that you immediately get that gas shut off to perform the repair. In water main applications, we can use mechanical fittings and other mechanical connections that can be used where there's water in a break of that nature. Of course, water main breaks don't happen at 9 a.m. on a Tuesday after you've had your coffee. They happen at 2 a.m. on a Thursday that's just before Christmas Day. So I know from experience that way. So those are just the repair manual is just a long guidance of different mechanisms that you can be able to replace and repair this material.
Key message on repair, though, to our audience is you repair polyethylene just like you repair other stuff. You got one of those Hymax band clamps, use it, put it around the polyethylene. We would like you, if somebody comes in and uses those excavator teeth, that bucket, to rip the heck out of polyethylene, which happens, just put a band clamp around it, or better yet, take the time to drop in a spool piece using electrofusion couplers. George Fisher makes a great product called the multi-joint. They've got a variety of different products based on your need. Keep some of those around in whatever diameters you need, and you'll be just fine. Remember, you fix polyethylene just like you fix other stuff. The thing is, it just doesn't break as much. Hayes and Williams factor, 150 for the life of the pipe. So we're just like PVC in that regard. No tuberculation with either of the two plastic pipes, and our flow rates are just about the same. All right, got to get back to the screen here. OD conventions, IPS and DIPS. So in the municipal world, we're recommending DIPS, so it matches up with the ductile iron. IPS is also available. Just specify what you want. If you're in the water side, get some blue stripe pipe. Is it a sewer pipe? Get some green. So this is co-extruded. The blue stripe tends to be more available than the green, but call around to your distributor, see who's got what, let them bid it, and we will deliver whatever striping pattern you want. We're seeing a lot of purple these days on reclaimed water, and then of course red stripe for fire lines. So you don't see this sort of failure, this growth in polyethylene like you do in steel and ductile and cast. We don't have that issue. But what do we have? So here we have some exhumed pipe at 4 years. It's got a film on the inside of it. You can pig it. 10 years ago, we pulled this 41-year-old polyethylene out of a LyondellBasell plant in Europe. And there's a little scratch mark in the upper right-hand side of that polyethylene pipe. This pipe tested brand new. UKWIR, the same group that produced this study on their screen right now, published a document 2 months ago where they exhumed some 40-year-old first-generation polyethylene. It tested new at 40 years old, and they say they're going to get 160 years life out of that first-generation polyethylene pipe. Europe is much more advanced in their use of polyethylene than we are in North America. So we tend to get a lot of our failure data and a lot of our good long-term data from them. So here's a study that was produced 10 years ago now by UK Water, which is their version of AWWA or WRF, Water Research Foundation. And there on the right, we're going to look at the average, close up of the average. So cast iron was failing at over 40 times per kilometer per year. Polyethylene is about 8 times, whereas ductile and PVC are up around 13 times. So this was first and second generation and some third generation polyethylene, all pre-4710, all failure types, whether it was a bad fusion, third-party damage, tuberculation. There were 410,000 failures here in this report. I've read it. You don't have to. Here's the summary. Drew, what do you got?
Peter, we just had a question come in on the topic of failure and third-party damage.
Yep.
If your polyethylene line experiences a crossbore, what are your options for repairing that line?
Awesome. So the options for repairing are, first of all, you got to discover it. So where has that occurred? We recommend a spool piece. So close off your valves. If you don't, the valves are too far away and you don't want that many people to be inconvenienced, bring in some squeeze off tools. If you don't have squeeze off tools, you're going to have to use the valves. We would love it if you drop in some AVK Series 66 valves. So those would be, Drew, have those polyethylene pup ends on them. A lot of distributors carry those footage tools, so you can rent them from the distributors. I know ISCO carries a lot of them. I'm not sure what Footage's distribution is around North America, but we want to see a spool piece, Drew. And if it's a small enough hole, just drop one of those Hymax band clamps on it and come back in and do your spool when you have time. Alan, do you have anything to add to that advice?
Nope, you did pretty good, Peter. I really appreciate it. So just recognize in the operation of a utility system here, statistically, as more breaks happen on a certain section, the likelihood of continuing to break is going to increase dramatically. So the time period between the first and second break might be a couple of years, but by the time you get to the fifth and sixth, it's going to start breaking, every 6 months. So you got to make sure that you've got those target areas in place, and you stop it from breaking by proactively replacing it.
So you're talking about legacy materials.
Yes.
Yeah. So you said earlier that polyethylene, or maybe I did, doesn't suffer from cyclic fatigue. Can you tell us what that is and why polyethylene doesn't, but PVC does?
Yes. So cyclic fatigue is a long-term basis for failure of the pipe. The hydrostatic design basis that we're looking at in HDPE is proven through statistical analysis and testing that actually runs 10,000 hours on the actual pipe material to predict its failure. So because of the occasional recurring surge pressure resistance that the advanced HDPE pipe material has, we're able to withstand those operational parameters of routine valves or pressure surges, valves on and off, or all valves shut down in much more detail. So PVC doesn't have that accommodation of higher pressure surges within the material itself.
So it suffers from cyclic fatigue, and a lot of these failures in the 20 and 30-year-old PVC are cyclic in nature. Alan, I've got another question for you. It's an issue that comes up quite regularly, and it has to do with what I call ID matching. So the PVC people say, because they want their product to be smaller diameter than ours, because we're OD controlled, we have a thicker wall than PVC, because their product is actually stronger than ours, but it's also brittle. Can you explain why, from a hydraulic standpoint, ID matching, so that our ID doesn't have to match PVC? Why is that true or not true?
In a theoretical scenario, what they're looking at is just one pumping location all the way to one pipe all the way through to whatever end they're looking at. That's not the way distribution systems work. Period. Typically, you'd have either a water tower that provides a constant pressure through the pipe network. You have fittings within the pipe network that the friction loss across those fittings are actually substantially higher than the overall pipeline itself. In many instances, HDPE doesn't require as many fittings because of the allowable bend radius that we have. So we can get rid of those 11-degree bends and 22-degree bends when we're working with this pipe material in the field. So if we're just looking at ID comparison on a theoretical standpoint, where you have either a variable speed pump or single water tower and then single end user, yes, you would probably want to look at friction loss over the span that you're evaluating. However, that's not the way that complicated water distribution systems really operate.
I would like to say to our audience, we're right at 1 hour. Based on the content that we have left, we'll be done in 15 minutes. If we have a lot of questions, it could be 30, but my guess is we'll be done at 15 minutes after the hour. Thank you for staying on the call. All right, so UKWIR, the Water Research Foundation, has done a lot of research on polyethylene as well. We haven't planned to talk about that yet in this call. We have a lot of standards that we pay attention to, from the manufacturer of the product as well as the testing of the product in the field. This is just a cost of entry. Everybody does this. Doesn't make us any special, better, different than anybody else. But no, take it that the products are well tested, and we meet all the same requirements that other pipe materials do, like NSF 61, AWWA C906. It's all in there. And we're happy. We actually have a 50-minute session on this as well. So as far as accountability, if you're interested in using the product or are using it, what do we do to make sure that the product's going in the ground the way you want it to go? From a design standpoint, Alan, tell us a little bit about that engineer's package and some of the tools that are available for the design engineer.
Yes, the engineering package has specifications both in regular format and master spec format on open cut excavation, high density polyethylene pipe, horizontal directional drill and pipe bursting. There's a bunch of different typical details in order to be able to show how many different ways you can install high density polyethylene pipe, service connections, manholes. The Plastic Pipe Institute's handbook on polyethylene pipe is included, as well as a searchable PDF. So that makes a big difference in being able to be a great resource. I love the hardcover book. I still have one on my shelf, but a searchable PDF really makes quick research into it available to you. So we've also included a lot of technical notes and municipal advisory boards reports on all things high density polyethylene. So it's a wonderful resource available to you.
Yeah, I'll say it is. Hats off to PPI. We get to talk about it, but they're the one that did the heavy work to make it all happen. So from a design standpoint, the specs are available to you. We also have specifications directly related to installation method. So Alan has developed, Alan, do we have a separate one for open cut, or is it just pipe bursting and HDD?
Note we have open cut excavation. Absolutely talks about the backfill material required, compaction levels. Handling high density polyethylene in a traditional open cut excavation is no different than what you would do with ductile iron or PVC, except some of the productivity levels, such as being able to fuse the runs well in advance above ground if you can open up longer trenches all at one time. So that's a productivity item that really is a true benefit of HDPE. But you have to start with a good foundation and come up from the bedding and make sure that you're using proper compaction of good backfill materials through it. So we do have that as a spec as well, Peter.
So we don't give you ASTM 2321, which is your primary document for bedding, because you have to pay for that, and we're not allowed to give that out because of copyright reasons. But these specs are available to you in Word, so you can copy and paste at will. Should you just decide to send us your spec, just give us a week or two and we'll get it back to you. We will use track changes, and you can accept or reject whichever one of the changes that we make that you'd like. That is free of charge to you. On the engineering side, we say use the tools available. One of the things that Alan mentioned was we have fewer connections, fewer need. We don't make 11s or 22s. Why is that? Because we just bend the pipe. Alan, could you tell us a little bit about the bending radius of polyethylene, what the resource for that is, and why is it we can make it around a cul-de-sac when other materials can't?
The allowable bending radius is derived from a elastic property of the pipe itself. So we can temporarily bend and still maintain the structure of the pipe as we go through that. So I believe it's 20 times the diameter to be able to bend this around, or the DR rating for the pipe itself to be able to provide that. In many trenchless applications, the bending radius of the pipe is not the limiting factor. It's going to be the drill string and horizontal directional drill would be the limiting factor, and then the pull rods in pipe bursting would be the limiting factor as to what you could get across. But contractors understand the workability with HDPE, and in many instances can easily go around a concrete conflict box, utility conflict box on the backside of it, or kind of snake its way through third-party utilities just because it's so forgiving of a material.
So to your point about the rods and pipe bursting, so what Alan's saying is if you have a long, subtle bend, pipe bursting might work. But if it's somewhat sharp or an 11 degree, you're not going to get those rods to go through that. So that would be your start point or your end point in a pipe burst. So that would be where you would excavate to get through that curve. Alan, is that about right?
It's manufactured bend, so it's anything 22 degrees and higher. Typically,
Okay.
An 11-degree bend, we would, if we know where it is, we excavate and we remove that, and then you over excavate on either side of that, and you can get the quick lock rods through that manufactured bend itself. So, but yes, Peter, you're right on the money there. Manufactured bends, it's not going to get through. They become an excavation point for pipe bursting.
So Alan, this slide says no thrust blocks. So talking to people that really only know legacy materials, they don't believe that. You know, how is it you don't control a joint the way they've always controlled a joint? Could you help us understand that, please?
Absolutely. So a fully polyethylene system is a monolithic self-restrained system. So if you had polyethylene from your origination point where you provide water source all the way to the end where it connects to the house service connection where you're providing it, every bit of the polyethylene between those two systems then are self-restrained. So the soil column that is holding it into place provides ample energy and force to be able to restrain that pipe. It's when we connect to third-party bell and spigot systems that we are looking at restraining this pipe. So it's just like any type of modification to a pipe system when you're changing direction and therefore need to restrain the bell and spigot from pulling out. So any movement within the polyethylene system, when it's connected to a bell and spigot system, then could potentially pull that bell out of the spigot. And that's what we're looking to restrain when we do require thrust blocks. Mechanical adapters such as an MJ adapter, the flange, heavy duty flange that Peter had shown earlier and talked about, in some scenarios can be ample enough to be able to alleviate the need for a thrust block when connecting to other pipe material types.
Okay, so on the run from 1 to 149 versus 0 to 50, there are no thrust blocks, but there may be when we connect other materials because we're worried about pull out of legacy materials. So we also have on the accountability side of things something known as the data logger. This is made by McElroy, and this gives accountability to the owner through the inspector or the consulting civil that, hey, that operator's doing the fusions the way he or she is supposed to be doing them. Very cool machinery. We talked about it last week, had over 200 people on that call. But it's a second level. It's once you get into polyethylene, you realize why it makes sense. But until you really get into it, you're like, why do I need a data logger? But let's take a look at a data logger. And this is what a graph looks like, a good graph. But this is what it's looking at. So this first part right over here is called the bead up. As the bead grows, the pipe end is up against that heater plate right here, and you see that bead grow, and we have pressure in the hydraulic system in that McElroy butt fusion machine. Once we see that bead up, we take the pressure back to 0, and you see that line coming down here, and we call this the heat soak phase. So that's when we have 0 pressure in the system, that hydraulic system. So there's no pressure up against that heater plate. And that goes for, in this case, 3 minutes and 20 seconds. And then we do what we call the heater removal. So here we have heater removal. That's when we pull the heater out after we've heated those ends. And we have 15 seconds typically to bring pressure up into the system, pull that heater out, and close the ends, which we see right here where the fusion takes place. So we've pulled the heater out. We now stick those pipe ends together, and that's when the pressure is in the system, and that pressure is held in the system. So at close to 300 PSI pressure for that full cool time from 3 minutes and 20 seconds all the way over here to 10 minutes and 50 seconds. That's the proper cool time for that pipe segment. So it's really very cool. It's methodical. This data logger permits guided workflow. And I like it because if they changed out the operator that had bid the work and your inspector's there and he sees that the guy doesn't really understand how to use the data logger, guess what? He's not trained on it. He probably isn't trained on fusion. So you get to kick him off the job, bring the guy back whose credentials were used to bid that work, and you're good to go. Drew, do you have any more questions? I would love to get to some questions. We got 20 minutes left, but I know everybody wants to jump. But Drew, what do you have for me?
Give me just a second here, Peter. Well, we had a few questions about tapping and making service connections to
Okay.
polyethylene mains. So, what are your options for potable water service connections, Pete?
Potable water. Alan, why don't you take that and let's talk about electrofusion service saddles, like George Fisher corporations and whatever else you think, Alan.
Yep, there's a lot of different possibilities for service connections, either from mechanical fittings or electrofusion that really go right on the side of the pipe wall. And then from the actual, once the service connection is made, however it is that you're doing it, those are self-tapping. So they'll come in and actually go right into the pipe wall and remove that coupon as we go through it. And then you're able to run your water right as well. There was some talk about actually extending the main, and if we extend the main, I'm assuming that the new size of the pipe is going to be just as large as the main itself, in which case we'll look at cutting in new valves, either through a temporary valve that's installed like insert a T or insert a valve or something of that nature, and you can easily just cut right into the polyethylene pipe and remove the coupon. Or you can use what Ben Ferguson had talked about earlier with the squeeze off, if you don't have adequate isolation already in place through valving. So those squeeze off tools are really, really a good use to be able to isolate certain segments and cut the water off where you're going to install either a new valve or service connection or a new connection to a main.
So, Alan, I know we recommend using polyethylene services because there are a lot of ways to get to the house without digging up somebody's yard. But how do we, if our standard is copper and we're going to go with polyethylene on the mains, but we don't want to use polyethylene services, which there are plenty of people that do that, how do we connect a copper line to our polyethylene?
They have a transition coupling once you go either through a mechanical connection at the main or otherwise, and then there's a transition coupling that basically will grab the polyethylene and then attach it to whatever service pipeline that you're interested in installing.
Let's say we decide to do a pilot project, Alan, with pipe bursting, and it's water, and I am not going to have my neighborhood, that block face, go without water. So how do I set up temporary water, and how do I ensure that it's the first time I've done a pipe bursting job in town? How do I ensure that the guy hooks everything back up by 5 o'clock?
It's very convenient to actually put together a 2-inch above ground temporary bypass. So they'll fuse that 2-inch pipe run together, disinfect it, flush it, and then make sure that it can meet the pressure test before they install the service connections, the existing ones, to that temporary bypass. It's up to the contractor if they want to drill in alongside services in advance of this and make the switch over. But for pipe bursting, when we decommission the water main often at 8:30 in the morning, we start to insert the rods, push it through a 400, 500-foot run. You can, in many instances, be turning the water back on by 3 o'clock in the afternoon if all goes well. That includes all the service connections that are in between it. If it's not acceptable to have an outage period, then all those houses can easily be on the temporary bypass that can be installed above ground. You would take certain precautions, such as making sure that you ramped up over the 2-inch on driveways, or make sure that you had asphalt protection over top of that pipeline in very sensitive areas. They also have, for gravity sewers, they have larger HDPE temporary bypass systems to go from the upstream manhole to the downstream manhole and bypass the operation altogether. In some of those instances, they simply cap the gravity sewer at the clean out, go through the performing of the pipe bursting process during the day with an upfront notice to the homeowners to make sure that they minimize water use. And then after they perform the hard connection to the main, then they simply pull whatever clean out cap they use to be able to temporarily stop the flow.
Hey, Drew, how do we engage with a city that wants to try a pilot? They've never done polyethylene. How do they talk to us? What's the routine?
Well, our emails are right here on the screen, and we assist cities through that process all the time, from spec review to connecting you to qualified contractors and manufacturers. And we'd even come in and be on site and provide training to operators and your subs.
Alan, one final question. Thank you for that, Drew. The most popular way that people, cities, utilities first use polyethylene is because they use it on a drill. What is the proper way to connect up to ductile iron once we've completed that 400-foot drill?
So the way that you would connect to an alternate pipe material is to make sure that the HDPE is restrained either through a thrust block restraint, when you've got electrofusion fittings that we can put right around on the HDPE pipe to be embedded in concrete. Then a mechanical connection like an MJ adapter that goes straight into whatever your terminal connection is going to be for ductile iron. So if it's going into a valve, I would typically spec out valves on either side of a sensitive drill in that scenario to make sure that you can isolate that section. The MJ adapter can go right up to the valve that you're installing there.
Good job. And there's actually quite a bit of material at PPI's website and also ours as it relates to proper drilling procedures. Drew, are there any additional questions?
Just one regarding moving pipe around on a job site. Do you have to carry it? What's the best practice?
Alan.
Yes, you would protect it. Make sure that when you're taking it off the truck, you're not standing behind the truck. We make sure that the equipment that we're moving around with, the forklift doesn't have any burrs or other things that would damage the pipeline as we move it through. We put it in good stacks. Make sure that we don't exceed an allowable stack sizing chart. We'll talk about more in the above ground section next month. But then make sure that nothing is in the way there to provide an unstable surface as to which you're stacking the material on, and nothing in the way to be able to hurt the pipe as we see it being dragged to the site itself. Oftentimes in pipe bursting, you can drag it along the surface, and that will not exceed the 10% gouge ratio within the wall of the pipe. So PPI has analyzed that a 10% scratch or gouge within the pipe wall thickness, if it's less than that, it'll still operate within its lifespan as predicted. I'd say when in doubt, cut it out. So if you see something that you think might exceed that 10% wall thickness, you simply cut it out and then refuse the pipe, and it'd be pretty, it actually doesn't, it's not very time consuming at all. So we had another question on quality control on HDPE joints. I'm not sure if we fully answered everything within the context of this presentation, but there is guidance through MAB on inspection of high density polyethylene projects, as well as lots of other information available to you.
Hey, Alan, I'm going to answer that one and then we'll go. I think you better attend to what's going on in the background there. I'm a little worried.
Okay, thanks, guys.
Thanks,
anyway,
Alan.
so as it relates to inspection and quality control, all those distributors that I mentioned earlier have classes. So you can send your inspectors to learn about polyethylene. Both Drew and I are qualified inspectors, and we're qualified to teach that inspection class. You can go to McElroy to do it. You can go to Sandale or Consolidated or ISCO or Core and Main, and they will teach your inspectors how to be inspectors on polyethylene jobs. We recommend the data logger. We recommended the use of hydraulic machines, which permit the use of the data logger. So all that data can be incorporated into the cloud and you can track it over time. Drew, anything to add on that topic?
Not on that topic, Peter. I just want to take a moment to plug tomorrow's presentation, the 301, the engineer's view. We're going to get into a lot of design considerations. For those of you who are municipal engineers considering using poly, you'd get a lot of good material in tomorrow's presentation.
Yeah, that's also planned at 75 minutes plus questions. So that's awesome. Drew, good job today. Thank you, Alan Ambler, and a particular thank you to our guests for sitting here and listening to us for 75 minutes. It's so appreciated. Come back for more, and we will see you next time.
Hey, thanks, everybody. We'll see you tomorrow. Take care.